In Coulomb's law, E is equal to energy, K is equal to Coulomb's constant, and plus Q and minus Q are equal to the magnitude of the charges. R is equal to the distance between the two particles. On the AP exam, you will not have to do calculations using Coulomb's law, but you can use it to justify certain things. So it's important to know that as the magnitude of the charges increase, the energy also increases. And as the distance between the two particles increases, the energy will decrease. First ionization energy is the energy required to remove the outermost valence electron. First ionization energy increases as you move from left to right across the periodic table and increases as you move up the periodic table. Some exceptions to this rule include nitrogen and oxygen. Nitrogen has a greater first ionization energy than oxygen because it has a half-filled p orbital, which is more stable than oxygen's p orbital since it has some spin-paired electrons.
The magnitude of ionization energy can be estimated qualitatively based on Coulomb's law. So you do not need this equation. The farther an electron is from the nucleus, the lower its ionization energy will be. So fluorine, for instance, has a higher ionization energy than rubidium because it is so small, so the electrons are closer to the nucleus than with rubidium. The higher the nuclear charge, the higher the ionization energy of an electron in a given subshell.
Photon-electron spectroscopy is a method used to determine the ionization energy of a substance. Photon-electron spectroscopy is based on the photoelectric effect, which is when radiant energy knocks off electrons from a metal. The radiant energy act as tiny energy packets called photons, given by the equation, where E is the energy of the photon, h is Planck's constant, and nu is the frequency. A photon must have enough energy to overcome the binding energy of an electron in order for it to be removed from the atom. The binding energy of an electron is the same as the ionization energy, and it is the energy from the coulombic attractions of an electron to the protons in the nucleus. The shell model of the atom can be explained by photoelectron spectroscopy data. In photon-electron spectroscopy, ultraviolet energy, or X-ray photons, remove electrons from a gaseous sample of an element. The sample is a gas so that IMF forces don't interfere with the photons, and only electrons are removed. When energy photons hit an atom, only one electron is removed at a time, and electrons can be removed from any shell of the atom. So, photon-electron spectroscopy is not used to determine just the first ionization energies of an atom. When a photon hits the substance, the ionization energy of the electron that gets knocked off, plus the kinetic energy of the electron when it is moving through the analyzer, equals the energy of the photon, which is the equation h nu equals IE plus KE. This means that electrons that are easier to remove will have more kinetic energy once they are released from the atom, and electrons that are harder to remove will have less kinetic energy. A graph produced from PES looks like this, where the signal intensity on the y-axis is directly proportional to the number of electrons in the subshell of an atom, and the x-axis is the ionization energy. In the graph, the x-axis is usually from high to low ionization energy, unlike from low to high, like most graphs. The PES of lithium has two peaks because it has the 1s and the 2s energy levels. The peaks are different heights because the 2s level has one less electron in its shell. In this PS graph representing many elements, the ionization energy in the 1s subshell increases from hydrogen to boron because boron's most inner core electron has a pull from many more protons. The lowest energy peak is assigned to lithium because this peak is for its valence electron, which has more shielding than hydrogen and helium, and a lower effective nuclear charge than beryllium and boron.
Electronic structure can be inferred from evidence provided by PES. Both electrons in helium are identical and are about the same distance from the nucleus as hydrogen, except hydrogen only has one electron. There are two shells in lithium, and the outermost electron is further from the nucleus than helium.